it works. Are you ready, Jonathan? Okay, so the next speaker, Jonathan from Google, he's working on P4-based automated reasoning, and maybe he's our next user of P4-Spectag. With that, please welcome him.
Thank you. That's right. Clearly invited as a bribe, so don't expect too much from this presentation. I'll be telling you about some work that we've been doing at Google with P4-based automated reasoning. P4 here, you may not know, so just in case, super briefly, it's a programming language for network devices. That's most what you need to know, but when you start seeing me talk about switches, I don't want you to be immediately confused why I'm going into that. Okay, so I, of course, want to thank my team of collaborators. Stefan Smolka here is my direct manager at the moment, and Wakar was my manager before this. And actually, I would say was the person who made us able to do this at Google in the first place. Doing these kinds of exploratory projects can sometimes be a bit tricky in industry, as some of you may have experiences with. So I want to go back in time for about 8 years to tell you about some of the problems that motivated us to build this system. So Google needed to get a new generation of switches into their data centers. And in doing so, they had certain goals. The most important goal was for these switches to be very, very fast. Right? This is why we're updating to a new set of switches in the first place. And in particular, this means that there's a new ASIC, new hardware, that is, like a new chip, just in case, and new optics. One thing I meant to say in the beginning, please do feel free to stop me and ask questions. I no longer know if I'm saying industry jargon, so it's possible it slips in, and then you should be like, that doesn't make any sense. That's not a real world. Cool. The other big goal that we had, and I won't say too much about this, but we really wanted to be open source and industry aligned. And there's some very practical reasons for this beyond whatever moralistic reasons you might think of. One being, it makes it much easier to work with external collaborators. And another being, it means that if the world moves a sort of technology forward, we're not immediately left behind. Right? And that turns out to be a pretty big deal. We think we are very good engineers, for sure, and we have many of them, but we are not the entire world, arguably. Anyway, so the other big thing is silicon independence. And this is the one that I'm perhaps most passionate about. We'll also call this optionality throughout the rest of the talk. And the key here is that I told you that we're going to get this new ASIC with this new hardware. And actually, we would like to be able to just sort of swap these out. Not necessarily while they're running, but if we buy a new one, then we want to be able to just put that in. And if we start getting programmable ASICs eventually, this is a thing that's coming up in the switch community, you may or may not have heard of this, then we'd like to be able to just go in and use these in our data centers. So that was a very important concern. And finally, we need to move to a new SDN API. I'm not at all going to tell you about why we're doing that, but it turns out to be very important. And the SDN here is software-defined networking, another concept that you may or may not have heard of, but extremely briefly, if you learned had a networking class in your undergrad, you probably learned that networks were these big distributed systems of switches that all do their own little thing, and somehow they figure out how to make the internet work. We don't do that. Think of switches in our data centers as being extremely dumb, maximally dumb, and there's instead a centralized controller that figures everything out and programs those switches to do the things that they want to do. That's really what's going on. Okay, and in the end, of course, we need to actually deliver a data center fabric. Otherwise, all of this work was useless. So in an ideal world, it would be great if we could just do all this work sort of serially, right? Because then you know what dependencies do before you have to write the things that depend on them. In the real world, that turns out to be unacceptable because by the time 10 years rolls around, you kind of have new ASICs and new optics. And the old ones are no longer fast, right? So instead, you have to do all of this at the same time. And for any given layer now, you kind of have new capabilities that they're kind of figuring out come from below, and new requirements that they're kind of figuring out they need from above, which makes it pretty tricky to design all of these. And in the end, 3 years in the future, you need to deliver this production-grade data center that I told you about that's at least as reliable as the current generation that we've been using for 10 years. So how do you possibly do this? Well, I think there's a key trade-off space here, and that's what I'm really sort of here to talk to you about today, which is there's a trade-off between reliability and feature velocity. And what do I mean here when I say feature velocity? I told you that sort of requirements and capabilities change over time. That means that you have to change all of these things throughout this period, right? You're sort of exposing new features. You learn of a new thing you need and you expose new features. If you want to do that fast, this is feature velocity. Okay, it turns out in isolation, we know how to solve both of these problems really well. For reliability, you just write lots and lots of tests. That's great against the spec. I recognize that this community doesn't believe that that's reliable, and I think that's perfectly reasonable. But in industry, that's a gold standard. All right? So you want to write lots of tests against the spec. But if you want maximal feature velocity, actually you just don't want to test anything at all. Because now you can just change a feature, you can add a new one. Great. I mean, your data center crashes, but you definitely added that feature. So the reason why these are sort of in contention is that every time you add or change a new feature, all of these beautiful tests that you just wrote have to come and change. And so that just means every additional feature that you add, every additional test that you add, costs you a lot. So there's kind of this nice, it's not really a curve, line of manual testing. And of course, you can move this line. You can just throw more money at the problem. You hire more engineers. Probably there are diminishing returns. I'm not going to touch on that in this talk. But you could imagine that you could move it. But wouldn't it be great if instead there was some sort of magical way to be in that top right corner, where you just have kind of a comprehensive set of tests that appear magically for any new or modified feature that you use, where your tests just change when you change the feature, right? That sounds amazing. So amazing that that's, of course, exactly what we do. And how does this work? The specification part here is the key. And really, it's by making the API, which is how we expose these new features, and the tests come from the same language. That's really the key insight. So if you know anything about P4, and you don't need to, but if you did, you would think that the way we use P4 at Google was very strange. Because what it's really designed for is as a way to program a programmable network ASIC, kind of what I told you in the beginning. Instead, none of our network ASICs are programmable, more or less. Instead, they're what we would call a fixed function network ASIC, and we just use P4 to model their behavior. And then we say, well, the ASIC should abide by this model. What does that buy us? Well, actually, if you think of these P4 programs now as these machine-readable specifications, they just have to capture the requirements for a particular switch in a particular deployment role. If you know data center networking, and again, you super don't, then these are sort of three very common types of switches that you have in a data center. Top-of-rack switches, middle blocks, and fabric border routers. This is the only P4 that I'm going to show you throughout this entire talk. So I'm going to really make sure I explain it moderately well. The interesting thing about all of these switch deployments is that they're embarrassingly simple. There's very little stuff you need to do here, and particularly with the middle block, which is why I'm choosing that as an example. The middle block really just routes traffic forward, basically. And so the thing that you need is some sort of table, like an IPv4 route table, that matches on a packet, its IPv4 destination, for example, and takes some action. And this is a very common abstraction in the networking space, something called a match action table, right, where you match on some packet feature and maybe some metadata, and then you take some action that probably modifies that packet or some metadata. And so this is kind of our main requirement for the P4, for the middle block, and that's a very simple requirement, but it gives us two very powerful things. Number one is it gives us a schema of the switch API. It tells me exactly, as an SDN controller, what kinds of table entries I'm allowed to install on this switch. How am I able to change its behavior in how it forwards packets? And so for example here, I'm forwarding any packet that starts with a 10 in the IPv4 destination to port 42. But it also tells me what that actually means, right? It gives me the data plane behavior that's expected given some set of table entries. So if I'm actually given such a packet, then whatever port it ingresses on, it should go out port 42. Right? So it tells me what this behavior is. And this lets us do some cool stuff. Because the SDN controller now has this extremely simple view of what it means to be a middle block switch, right? It's this very simple API where it just does L3 forwarding, IP forwarding, and load balancing, let's say. And the switch ASIC is actually this crazy, complicated beast of a machine. It can do almost anything that you want it to. It has infinite configuration knobs, and no one knows what a large set of those configuration knobs do when you use them together, but you sure can if you want to try. Which makes it very powerful. Anything you can think to do, it can usually do, but very, very unpredictable, right? Very hard to test that this is doing the things that you really want it to do. But I just told you we can capture these requirements with this nice P4 program, and that gives us this schema. That we can just restrict the switch access to only use this schema. And now we only really need to test this schema because we know that no one's allowed to go in and fiddle with our switches behind our backs, in some sense. And so this gives us this embarrassingly simple API that's extremely predictable because I just told you that it makes this, gives you this data plane behavior that's completely specified in a machine-readable fashion. And I'll tell you how this P4-based automated reasoning comes into it being predictable in a real sense as well. So now, the SDN controller has this sort of beautiful view of what the switch really is, right? There are two additional benefits. One of them I kind of told you about before. Well, actually, both I did, I suppose. One is velocity, right? As soon as I change this P4 program, which is the only way I'm able to expose any new feature, because literally otherwise you cannot use it, then I automatically am going to get this extremely predictable behavior. And also it gives me optionality, right? Any switch ASIC that can implement this API is one that we can now buy. And if you're a vendor and Google says we can buy your switches, well, now you're a vendor. Like that's all you would need to be a vendor in some sense. So how do we get this reliability that I was talking about? Well, the key thing is very, very simple. We do diff testing. So in what sense is P4 an executable specification? Well, in the sense that there is a simulator that executes it. So this is called BME2. We did not build this. This is an open source thing. There's the P4 runtime is the name of the type of API that we use. And this simulator speaks P4 runtime and does data plane behavior. The actual switch also speaks P4 runtime because we built that part of it, and also has some data plane behavior. So what we start by doing is we program the same table entries on the simulator and on the switch. We take some input packets, send them to the switch, and now we get actual output packets. This is the real behavior of the switch. We also send them to the simulator. We get the expected output packets, and we check, are these the same? And that's pretty much it. Now there's a key question you should have here. How do you get input packets that are interesting? Let's say I only send to 0, 0, 0, 0. Now, like, yes, I mean, that would be correct in the switch probably, but it wouldn't really tell me much about the traffic that I actually care about. What we do is use this symbolic execution. So we have this tool we built called P4-Symbolic. There are now actually other open source tools that also sort of do this. Ours is ostensibly open source, but it's sort of open source. You can see the code. You can see the code. Anyway, but P4-TestGen is a very great open source tool that will also do this if this is something you were interested in doing. But this lets us generate these input packets given these table entries according to some goal. So if you think of P4-Symbolic as being able to say, I want to hit every single table entry with at least one packet, and for each of those, I want it to drop once, and I want it to be forwarded once. And that's pretty much exactly what we actually tell it to do, but that's the sort of thing you can say. So that's kind of the brain of the operation, if you will. OK. It's possible that everyone here knows how symbolic execution works, but I feel like I would be remiss in case I didn't say it, at least at a very basic level. So imagine you have this extremely simple program where you have some input X, you have a couple of branches, and then you can do 3 different things. You can ask your symbolic executor, give me the input that's going to trigger do B. It's going to go through and turn your input into a symbolic input, and it's going to collect constraints about what it means, like what has to be true about that input in order for you to get to each of these different branches. And then it's going to try to solve how do I get do B is reached? How does it do that? Well, it computes this path, grabs the constraints, solves this equation. We don't need to build these sorts of things. There are plenty of SAT solvers in the world. Use Z3, use anything else. X equals 1 is the solution. Great. How does this look in our world? Pretty much exactly the same, except the input X is a little bit more complicated in that it's some big packet. Tables now are these big sets of branches, basically. Each table entry is kind of one if statement where it takes some action. There's these other if statements in the program, and there's more tables. But I want to say, I want to hit entry 2, and you do the exact same thing morally that I just told you in the previous slide. So that's it. That's the secret sauce. Trivial. Things that you have known how to do for ages. Made a huge difference. We found more than 340 unique forwarding bugs. This is by an extremely conservative measure, because I only checked the most recent numbers a couple of days ago, and the liberal measure was about 1,500, and I didn't want to go through all of those. So I figured that if I just look at the ones that they really fixed, but in a proper way, and then the ones that are still open, that's a conservative measure. And less than 5 forwarding bugs that we are aware of have sort of escaped our detection, in the sense that they were caught at some later stage by other methods. Of course, I cannot tell you how many were never caught, because I don't yet know about them. But hopefully few. I guess that's the hypothesis. This has also been used for every data center deployment role since 2020. And perhaps most importantly, and I think this is kind of what Michael was also getting at, right? We don't get these nice statistics to update as much anymore, because of course a lot of bugs are now prevented before they ever get into production or into any sort of testable state by us. Because these are now very well trusted, and everyone pretty much has to run them before submitting anything substantial. And that's pretty much all I wanted to tell you. So wrapping up, we derive this kind of restrictive APIs from P4 specifications. The APIs admit automated testing. The testing evolves effortlessly with the API changes. And so that gives us this very nice trade-off triangle, but now you can suddenly pick all 3. And that's the nice part. All right. I'll give you some resources in case you're interested, but otherwise I will take questions.
Question? It's okay. So Matthew.
I will push the limits of my networking knowledge with this question. So to what degree are you doing flow-sensitive kinds of routing, or is it all simple table-like stuff, or is it packet inspecting stuff? Or?
Like in Google?
Yeah.
So here we come to these points where I never quite know what I'm allowed to say. To some extent, are we doing flow-sensitive routing? And it turns out you can test some of these things too. But this is, what I've told you about now, is very much on a per-switch basis. So some of these properties that would hold between multiple switches don't really get, I mean, I guess we're over-approximating possible behaviors in that sense, right? Because we're basically saying, well, this could send you anything, even if we know actually it couldn't send you anything.
Thanks.
Yeah.
Hi. So you talked about the 5 bugs that you didn't find that came later. Do you have a sense of lesson?
There were 4 bugs.
I remember the number, not the semantics
yes,
around
sorry.
the number. Do you have a sense of given the tool you have, you're actually at the boundary of where you should be, and the other bugs are doing it a different way, and you were not meant to find them? Or do you think you've got more work to do on the particular tool you have?
Both, in some sense. There's a tragic trade-off in industry where there are always infinitely many things to do, and you kind of just have to pick the ones that you think are going to find the most issues. Now we've found a lot of them, so we're moving on to higher level network verification and not doing as much of that interesting stuff. But definitely some of these bugs, if we made some improvements to the tools, we would have been able to find. These were not unfindable bugs in that sense. Yeah. Sometimes what ends up happening, the ones that are perhaps the trickiest, are when they are masked by the table entries that we have. So it turns out it was impossible to exercise this particular feature given the set of table entries that we actually use in production. Those are the sorts of bugs that we, with this particular method, have trouble finding, partially because we do this kind of table entry coverage thing instead of path coverage where we could say, randomly delete some table entries and let's see what happens.
The last question.
Yeah, and also about those less than 5 bugs. Can you say a bit more about where those bugs were? Like, was the model just not matching the hardware, or so was the problem that the testing you described wasn't sufficiently exhaustive, or like some part of the P4 model was wrong, or I don't know, how much you can go into detail there, but that would be interesting.
Yeah, good question. So one thing, I would potentially recommend this paper just for, it actually has a breakdown of the first 130 of these bugs or something, and what components did we find them in, which is kind of cool. One fun thing is 10% of the bugs roughly were in our P4 model. We were just like, oh, we wrote the specification wrong. I mean the 5 ones which did. Yeah, I know. But so that's but there were not yet any escapes, so it doesn't cover those bugs. For the 5 ones, it wasn't that the model was wrong, because we would still sort of consider that a bug. Well, okay, actually, in one case, it did turn out that the model was wrong, but it was unfindable, given the set. It was usually the limits of the way that we do the testing. So kind of like I was just telling Felipe, right, where you have, we often use this set of entries that we think are very representative of what we actually use in the data center, because we literally install them in our data center. And so it turned out that sometimes there are just behaviors that those can't exercise. And
the data center changes, and then we do exercise them, and then it becomes a bug.
Yes.
If it doesn't have a data center, it's a bug.
That's right. But that's exactly right. Yeah. So then it changes, and this is why we try to tell all of our colleagues that just because it's not a production use case now doesn't mean it shouldn't work correctly. And so if you saw this sort of set of open bugs that I had, anyway.
Thank you. Yeah, let's thank him again.
Thanks.
We are gonna get to the last